Hello everyone, this is the first chapter in Unit 2, which is all about linear regression, and Chapter 6 talks about scatter plots, association, and correlation. To begin, we'll just talk a little bit about scatter plots. So scatter plots are the most common and most effective displays for data. And in a scatter plot, we're able to see any patterns that might be in our data, trends, relationships, and maybe even some extraordinary or outlying values that stand out from the majority of our data. Now, in Unit 1, we talked about univariate or one variable data. And when it comes to scatter plots, we're now looking at two quantitative variables. If you remember, when we talked about one variable data with graphs before, we talked about SOCs, talking about shape, outliers, center, spread. When it comes to scatter plots, which again has two variables, two quantitative variables, instead of SOCs, we're now going to talk about DUFs, D-U-F-S, and these stand for direction, form, strength, and unusual features. So I'm going to talk a little bit about each one of these. The first one, like I said, is direction, and that is basically as we go from left to right in our graph, is there a positive direction or is there a negative direction? So if we look at this example in the year 1970, the predicted error, if you were to take the average of them, is right around 500. Whereas if we go down to 2010, it's right around 100. So as we move from left to right, we are decreasing along the y-axis. On this scatter plot, we would say our direction is negative. If you're familiar with slope, you've talked a lot about slope in Algebra 1 and Algebra 2. We would draw a line through this scatter plot and see that the slope is negative. That again tells us that our direction overall is negative. In this scatter plot, the two quantitative variables we're looking at are central pressure and max wind speed. And what I want you to do, pause the video here for a moment and tell me what is the direction that we see in this graph. Okay, so hopefully you took some time. Because we are decreasing as we move left to right along the y-axis, we would say our direction is negative here. After we talk about direction, the next thing we want to talk about is form. Now, when I say form, typically what you can think of that as is what is the shape of our scatter plot? So do we have a curve in our graph? Is it a straight line? Is it kind of exponential? So when I say form, typically we want to know, is it a linear association or is it nonlinear? We could get into more specific, like is it parabolic, is it exponential, and so on. But for our purposes, we just want to know, is there a linear pattern or is it a nonlinear pattern? So if we look at this example, because there's a generally consistent downward trend in a pretty linear fashion, as I've written this line here, we could say there is a negative linear association between central pressure and max wind speed. If you guys think back to Algebra 1 when we talked about y equals mx plus b form, you probably remember that is a very convenient way to see patterns. It's a very consistent rate of change and that kind of thing. We probably won't talk a lot about this year, but if the relationship is not straight within our scatter plot, we are sometimes able to modify taking logarithms or exponentials of one or both of our variables, and that will straighten out our data. But for our purposes right now, we're just going to work with either linear or nonlinear patterns. Ultimately, what we want to do, not this chapter, but in the next chapter, is if we have a linear relationship, we want to find a line of best fit formula. Now, if we look at this scatter plot, I think we all would agree this is a very nonlinear pattern. So just make sure before you find a line of best fit formula, or if you start talking about linear patterns, make sure that your graph actually shows a linear pattern. In this case, we do not have one. So up to this point, we've talked about direction. Is it a positive pattern or is it a negative pattern? We've also talked about the form. So is it linear? Is it nonlinear? The next thing we have to talk about is strength. So strength, that refers to how compact or how clear is our pattern within our scatter plot. So at one extreme, the points appear to follow a single stream like we see in this moving quadratic shape. we see that there's a very, very straight, very clear quadratic form here, okay? So because the points are very in line with one another, we would call this a very, very strong association. On the other hand, we can also talk about a very weak association. So if it's the case that the points appear as a vague cloud or there's not really a discernible pattern or trend in our scatter plot, we would say that is a very weak association. So as you can see in this scatter plot, can't really tell, is it linear, is it nonlinear, is it positive, is it negative? So because it's randomly scattered, this is about as weak of a correlation as we can get. In a little bit here, we will quantify or assign a number to how strong our association is. After talking about direction, strength, and form, the last thing you have to address when talking about or describing a scatter plot are any unusual features. Now, this is very similar to the outliers we talked about before, but because we have two quantitative variables, we're just going to refer to them as unusual features instead of outliers, but it means essentially the same thing. So if we look at this scatter plot, we see that most of our heights and weights, that's what these points represent, are going in an upward direction. So we see as weight increases, typically so does height. But then you see the 4 points on the bottom right, and those would be considered relatively uncommon. So here we have some, whatever this data accounts for, they're in the 30 to 40 pound range, but they're only about 10 inches in length or height, okay? So that group of 4, something fishy is going on there. So we would consider these to be unusual features. So when you're describing a scatter plot, in terms of unusual features, you would just want to make a point of this cluster of group of points that's in the bottom right of our graph. Next, when it comes to our scatter plots, sometimes we need to figure out what is the role of our variables. So because we have two quantitative variables, one is going to go on our x-axis, one's going to go on the y-axis. And what we need to determine is which one is our explanatory variable and which one is our response variable, okay? So when the roles are clear, so if we know for sure that one is likely to influence the other, we call the explanatory or predictor variable as our x variable, and then our response variable is going to be our y variable, okay? So if we talk about this example where we have a variable of time spent studying and the test score that you get, you might ask yourself, which one is more likely to explain the other? So if I know that I'm going to spend a set amount of time studying for a test, is that going to explain what my test score is? Or if I know that I'm going to get a 90% on a test, does that determine how much time I'm going to spend studying? Well, in this case, time spent studying probably does a better job of explaining your test score than the other way around. And that's why I've got time spent studying on our x-axis, because that would explain or help predict what the test score is going to be, which is our y variable. So ask yourself, what variable best determines the outcome of the other one? And the one that determines the outcome is going to be on our x-axis, whereas on the y-axis, that's going to be our response variable. So keep in mind, just because we put a variable on our x-axis, that does not necessarily mean that it will predict or explain what happens with our y variable. So for example, in this bottom left scatter plot, we have internet usage on our x-axis, and we believe that would help explain your age. Now, this does not mean that if you spend 15 hours on the internet per week, that you are automatically going to be 25 years old. That doesn't make any sense, okay? But what we do see is that as you get older, as your internet usage goes up, your age typically decreases, okay? So internet usage, that can help explain your age, but it is not the sole reason why you are getting younger or older, okay? And then, of course, on our our right scatter plot, we have fresh lemons imported to the USA from Mexico on our x-axis, and on our y-axis, total US highway fatality rate. Are those two related in any way? Definitely not. So this just really hits home the point that just because you put something on the x-axis, it does not mean that it determines the outcome of our y-axis. So our next topic that we're going to talk about is correlation, and I'd mentioned this a little bit further back, but in this scatter plot, what we have is a collection of data on statistics students, and we've got their heights and their corresponding weights. And I want to know, how would you describe the association talking about DUFs, or direction, unusual features, form, and strength? So talk a little bit about that, take some time, pause the video, and then we'll give you the answer. So in this case, I would say that this is a relatively strong association because most of our points, not all of them, but it shows a pretty clear pattern in terms of what direction we're going. So I'd say it's a strong pattern. We've got pretty condensed points there. Also, I would say it's positive because as the height increases, in general, so does the weight of each student. It is a pretty linear pattern. Now we've got a few unusual features maybe, but in general, if we were to draw a line through our data, we could say this is a relatively linear pattern. And then of course, we do have one unusual feature at about 71 inches. There's a 280-pound person, and that would be considered unusual because it breaks away from the rest of our data. So we could say there's a strong positive linear association between height and weight, and there's one unusual feature at about 71 inches and 280 pounds. So in my description, I talked about how we had a strong association here, but sometimes, a lot of the time actually, we want to quantify just how strong an association is. So is it stronger or less strong than what we've seen in the past? So where we get that number from is from correlation. So this is our equation for correlation, or the correlation coefficient. We denote this with the letter R. I'm not sure where that R comes from, but if you ever see R, just know that that is our correlation coefficient. And what that number does is it gives us a numerical measurement of the strength of a linear relationship between two quantitative variables. So a couple of facts about correlation, or our R value. The correlation is going to range between -1 and +1. So we can't have any R values outside of that range. The closer our R value is to 0, the weaker the linear association is. So if you look at this out of these 4 scatter plots, the bottom right one, if we had an R value close to 0, there's not really a clear pattern there. So it's kind of random scatter. That would be an R value close to 0. The closer to 1 that correlation is, the stronger the association is. And then if we have a positive correlation, that indicates that we have a positive direction in our data. And if we have a negative correlation value, that indicates a negative trend in our data, or a negative direction. So again, if we have an R value exactly equal to 1, as we see in this top left graph, that means we have a perfect straight line in the positive direction, okay? And then to the right of that, if we had an R value close to 1, but not equal to 1, it's still going to be a strong linear pattern in the positive direction, but it's going to be not quite as straight as it was when R is equal to 1. On the bottom left, if R is close to -1, but not equal to -1, the negative indicates that it's going to be in the negative direction, as we see here, it's going down from left to right. And because it's close to -1, it's still going to have a pretty clear linear pattern. And then finally, on the bottom right, if R is close to 0, that's going to be a weak or no association. So we can see no real clear direction. We don't know if it's positive or negative, and we also don't see much of a linear pattern. So going back to our height and weight example from before, if I were to calculate the correlation, our R value, or our correlation value, would be 0.644. So what does that tell us about our association? First of all, it is a positive R value, so that means we have a positive direction, and I think we agreed to that before. We see it's going upward from left to right. Because 0.644 isn't really that close to 1, we wouldn't say it's a really strong association, we could say it's moderately strong because 0.644 still relatively close to 1, but not super close to it. So because we have a correlation of 0.644, this tells us that there's a positive, moderately strong linear relationship between height and weight. So one note on correlation, a lot of people throw out the word correlation when really they mean association, okay? What do I mean by that? Well, correlation, it measures the strength of a linear association between two quantitative variables. So for example, in this bottom right scatter plot, we see that there's a very, very clear pattern. It kind of looks like a parabola. And what a lot of people would want to say is, oh, there's a strong correlation between these two variables. But because it is not a linear pattern, we would say there's a strong association, not correlation. Because again, correlation, that is reserved strictly for linear relationships. So actually, if we were going to calculate the R value of our bottom right scatter plot, it would be really, really close to 0 because there is no linear pattern. So keep that in mind before you jump to using correlation. Make sure you have a somewhat linear pattern. And in general, before using correlation, you want to make sure that both your variables are quantitative. You also want to make sure that you have a relatively straight association, which the bottom right clearly is not. Also, major outliers in your scatter plot can really throw off your R value. So make sure that you don't have any major outliers before you calculate that R value. So a couple of things when it comes to correlation. Correlation treats X and Y symmetrically. Basically what that means is if we were to flip our X and Y axes, so X turns into Y, Y turns into X, our correlation value would stay exactly the same. Correlation also has no unit, so it's just R equals some number, and that number quantifies how strong our linear pattern is. Correlation is not affected by changes in the center or scale of either variable. So if we change our x-axis, which was in pounds, and we change it into kilograms, that would not affect our R value. And correlation depends only on the z-scores, if you look back at that formula, which you don't need to know much about. And they're unaffected by changes in center or scale, okay? Just a general guideline in terms of what's considered strong or weak or moderate. I've got this table here. So for a strong relationship on the positive end, it'd be 0.8 to +1 for our correlation, and then -0.8 to -1 on the negative side. For a moderate strength, we'd say 0.5 to 0.8 or -0.5 to -0.8. And then a weak association would be 0.3 to 0.5 or -0.3 to -0.5. And anything between -0.3 and +0.3, we would say there's very little or no correlation. Just a couple more properties. So correlation, like I said before, measures the strength of a linear association. And variables can have a really strong association, but have a very small correlation if that association is not linear. So going back to that quadratic problem that we saw before. And correlation is sensitive or non-resistant to outliers, because even if you have one single outlying value, it can really goof up our correlation overall. One really vitally important thing moving forward in this class is to realize that correlation does not mean causation. So just because you see a really strong linear pattern between two quantitative variables, it does not mean that the outcome of one of our variables determines the outcome of our other variable, okay? So we're not proving anything with just a scatter plot. And scatter plots and correlation coefficients never prove causation, okay? And if we ever have a hidden variable that stands behind the relationship and determines it by affecting the other two variables, it's called a lurking variable, okay? So that's where you're only accounting for two variables on your scatter plot, but there's some third variable that is the true reasoning behind why we're seeing a positive or a negative pattern in our scatter plot. And we'll see an example of that here in a moment. So this is a slightly different type of two variable graph, but what we see here, the two variables in questions are number of people who drowned by falling into a swimming pool and how well it correlates with the number of films that Nicolas Cage appears in. We've got a correlation value of 0.66, which is a moderately strong correlation. Now, I think we all could agree that these two variables are not in any way associated with one another. So this is just hitting home the point that correlation, just because these two variables are correlated, it does not mean that they cause one another. So Nicolas Cage being in a movie does not determine how many people are going to drown by falling into a swimming pool, or vice versa. Here's another example. So in red, we have per capita cheese consumption. So on average, how many pounds of cheese that people eat each year. And then in the black, we have number of people who died by becoming tangled in their bed sheets. Here we have a correlation of 0.947, which is a very strong positive correlation. But again, I think we all could agree that these are not causing one another. Maybe they are. No, they're not. I don't think. I can't think of any even offhanded reason why they would be related to one another. So just again, because they're correlated, that does not mean that they cause one another. And my favorite example of why correlation does not equal causation. In red, we have the divorce rate in Maine. So per 1,000 people, how many couples are being divorced? And in black, we have per capita consumption of margarine. Okay, it's like the fake butter. Our correlation here is R is equal to 0.992. So it's almost a perfect association, okay? But just like we saw before, this is almost certainly not related. Maybe you can come up with some storyline of why they might be created, but main point here, correlation does not equal causation. Okay, I guess I'll throw one more on here. In red, we have per capita consumption of chicken, and in black, we have total US crude oil imports. Okay, very unlikely that they're related to one another, but still we have a correlation value of 0.899. All right, so moving ahead, when you start on the homework, just think about how do I describe a distribution? So think about DUFs, D-U-F-S, direction, unusual features, form, and strength. And then correlation, we have that spectrum of R values from -1 to +1. The closer you are to 0 with that R value, the lower the association is altogether. So there's probably not much of a linear pattern at all. Whereas if you have a really, really close value to -1, that would mean a strong negative direction for our linear pattern. And then an R value close to +1 would be a positive direction with a very linear pattern.